Today's lesson is going to be on exponential growth and decay. Now there are two types of exponential growth and decay. Well, not really, but kind of. The first is just normal exponential growth and decay, which is compounded at a certain interval, which is known as t. And then there's continuous growth, which is not compounded at one set interval, it's just constantly being compounded. It's kind of hard to explain, but it's just no specific time interval. That's all you basically need to know. There are two types of buttons you need to find on your calculator in order to do the problems today. The first one is just E, and it's below the arrows on TI-84 by 3, and it's the second divide. And the second one is E to a certain exponent, which is X. And you can find that button on the left of the 4, which is second natural log. Today we'll primarily be working with formulas, and the first formulas we're going to be working with are the formulas for normal exponential growth and decay. There are essentially two formulas, but they're basically the same thing. The first one is n equals n sub 0, parenthesis 1 plus r to the t. And in this formula, n is the final amount, n sub 0 is the initial amount, r is the rate at which it's being compounded, and t is the amount of time it's elapsed. The second formula is for compound interest, which is basically just deals with money. And it's the same formula, except it uses different terms, and there's another variable, n. And in this formula, it's a equals p, parenthesis 1 plus r over n, close parenthesis to the nt. And in this formula, a is the ending amount, p is the principal, or the starting amount you have, rate is the rate at which it's being compounded, n is the time it's compounded per a given time, which is usually years, and then the parentheses to the nt, and t is the amount of years that have elapsed. The first problem we're going to be doing today works with exponential growth, but it's compound interest, it's money. Now the problem is number 32, and it's about wages. Jasmine receives 3.5% raise at the end of each year from her employer to account for inflation. When she started working for the company in 1994, she was earning a salary of $31,000. What was Jasmine's salary in 2000 and 2004? If Jasmine continues to receive a raise at the end of each year, how much money will she earn during the final year if she plans on retiring in 2004? So this is just finding how much money she's going to have for each year over a certain amount of years, and then you're going to start with 1994 and go to 2000, so you're basically, so from 1994 to 2006 years, so T's going to be 6, not 2000, and then you're just plugging into the formula. So for this problem, we're going to be using the compound interest formula and plugging in the numbers we know, which is the starting amount is $31,000, and it is compounded at a rate of 3.5%, and the first part is going to be for 6 years. We're going to plug in the formula so that A equals 31,000, parenthesis 1 plus 0.035 over 1, close parenthesis to the 6. And I'll pause the video and solve. Then when you plug that into your calculator, you get that A equals 38,106.92, and you include 2 decimal places, it's dollars and cents. For the next two parts of the problem, it's going to be the same thing. You're just going to use the same starting formula we used for the last one, but 10, for solving for her salary in 2004. And when you plug that in, you should get that A equals 43,728.56. And then to find your salary in 2024, again, you use the same formula, but instead of 10 or 6, you use 30. And when you plug that in, A equals 87,010.6. So one of the common problems we'll be using these formulas for is half-life. Half-life is the time it takes for something, usually an element, to decay to half its original value. It's usually used for radioactive decay of different types, and also chemicals decaying in the body, like certain medicines. And it is decay, so it's going to be minus 0.5 for the rate. We're going to be using number 39 for this example, and it's about radioactivity, specifically radiocarbon dating. The problem is radiocarbon dating uses carbon-14 to estimate the age of organic materials found commonly at archaeological sites. The half-life of carbon-14 is approximately 5.73 thousand years. Write an equation modeling for the exponential decay, and how many grams of carbon-14 will remain after 12.82 thousand years if you start with 7 grams. So the equation we're going to have is n equals NO, because they don't give you either of those values. Then it's going to be parenthesis 1 minus 0.5. 0.5 is the rate since it's decaying at it's going to be half its original value, and the power is going to be t, which is going to be years over 5,730. Now it's going to be over 5,730 since that's the half-life, so for instance, if it's been going for 15,000 years, it will have been compounded 15,000 divided by 5,730 times. So you just put the total years in for t. So now all you have to do to find the amount of carbon left after 12.82 thousand years, when you start with 7 grams, is plug that into the formula. So the formula will become n equals 7 parenthesis 1 minus 0.5 close parenthesis to the 12,820 over 5,730. Now plug that into the calculators, and you should get that n equals 1.48, which makes sense because it's about two half-lives that have elapsed, so it's like divided by 4 in this case.
Our second two equations will be on continuous functions. Our first equation is of continuous compound interest, where a equals p(e) to the RT, where a is the final balance, p is the beginning or principal balance, e is the constant e, r is the rate, and t is the time. Our next equation deals with continuous exponential growth or decay, where n equals n sub 0 times e to the kt, where n is the final amount, n sub 0 is the initial amount, e is the constant e, k is the rate, and t is the time. The next problem we will be looking at is number 36 on page 176. The pressure of the atmosphere at sea level is 15.191 pounds per square inch, or psi. It decreases continuously at a rate of 0.004% as altitude increases by x feet. A. Write a modeling function for the continuous exponential decay representing the atmospheric pressure, A, x. For A, we will be modeling the equation for continuous exponential decay due to the rate being negative. So n will be n sub 0 will be 15.191, e will be e, k will be negative 0.00004, and t will be x. B is next, which states, use the model to approximate the atmospheric pressure at the top of Mount Everest. Since Mount Everest is 29,035 feet above sea level, we will plug that in for x. Once you plug all of that into your calculator, you should end up with 4.76 psi. That concludes number 36. Now we'll be looking at number 31, which reads, worldwide water usage in 1950 was about 294.2 million gallons. If water usage has grown at the described rate, estimate the amount of water used in 2000 and predict the amount in 2050. For 31, we will only be looking at letter B due to its continuity. We must now plug in 0.0305 as the rate into the continuous exponential growth function, along with n sub 0 being 294.2 and t being 50. If you plug that all in correctly, you should get 1,351.89 million gallons.